Okay, let's move on to our last talk. We're delighted to have Robbert Dijkgraaf, the director of the Princeton Institute, to tell us about Michael Atiyah's dream for the geometry of quantum physics.
Thank you so much. It's a great pleasure to be with you. Of course, I would love to have been here with you in Cambridge. I hope you can see my screen well.
We can. Yep.
So my talk will be perhaps of a slightly different nature. It will definitely be in the spirit of Michael, and also I'm aware that at least you in Cambridge are quite close to the wine reception that will follow. So it will be a little bit of a more broad-brushed description of I think something that Michael himself would really enjoy. Of course, you know, it's a particular great pleasure to speak at this event from the Institute for Advanced Study. Michael Atiyah had a long affiliation, of course, most prominently as a faculty member for 3 years in the School of Mathematics, but he was a frequent member and visitor. And in fact, this is the notification of in the notes of the School of Mathematics deciding to extend an invitation to Atiyah in March 1955. Of course, as Michael said, the moment he actually arrived at the Institute, both Einstein and Gödel, Einstein and Weil had passed away, and of course von Neumann, which is also absent in this meeting, spent of course a lot of time in Washington. But of course, it was a wonderful opportunity for this kind of young gang of mathematicians, as we heard today in a wonderful talk by Nigel Hitchen, to start basically this revolutionary period in mathematics. Here are some pictures from the famous Louise Moore's photo album. Louise Moore's was a fixture at the Institute, and they had these wonderful math dinners. And one secret was you always cooked the same dish. And so, but that's a wonderful archive for us to see the long history of mathematics at IIS. Now, my talk is inspired by this kind of famous poem that Atiyah wrote, Dreams, about the nightlife of mathematicians. As he said, without dreams, there's no art, no mathematics, no life. I was almost myself very much inspired by these words. And it reminded me of a wonderful essay written by the famous biologist François Jacob, Nobel laureate, who wrote about courage a few years ago in the French Academy of Sciences. Of course, he himself was very courageous, being fighting in the resistance during World War II and being a path-breaking biologist. And this piece he writes about what he called science by day and science by night, saying there are two different modes in which the typical scientist can be. It's quite eloquent and evocative, this article. I can really recommend it. And he writes that, you know, when we are probing in the night, we are traveling through this labyrinth in our mind, searching for a sign, a wink, an unforeseen connection, like prisoners in a cell. We walk around, and he also mentions that you know, what guides us in that way is intuition, and as he said, courage to go beyond that. But often, of course, when we publish our works, we forget the night science and only talk about day science, and often said that any mathematical article is written in opposite chronological order, starting with the clarity of mind that's usually only the outcome of the whole process. This labyrinth of the mind evokes, of course, Galileo's famous description of the book of nature, where, you know, we are wandering around in the dark unless we are, in studying nature itself, are enlightened by mathematics. Now, there's a long series of quotes and remarks of famous scientists about the relation between physics and mathematics, would be my theme in this lecture. This is the famous one by Richard Feynman, who wrote that to those who do not know mathematics, it's very difficult to get across the real feelings to the beauty, the deepest beauty of nature. If you want to learn about nature, you have to understand the language that she speaks in. Now, Feynman also famously said that if all mathematics disappeared today, physics would be set back exactly 1 week. And this trouvaille, I think, is well remembered. But I must say, I want to thank Michael Atiyah by his kind of famous riposte. That was the week that God created the world. So I would say math, physics, if it would be a soccer game, it would be 2-1. And math is in the lead. Mathematics have, of course, been various ways to approach mathematics. We can approach mathematics as a Platonic science. It's the famous saying by Sir that I don't think he ever dared to say himself, but he whispered it to Raoul Bott, and Bott quoted it, that while the other sciences search for the rules that God has chosen for this universe, we mathematicians search for rules that even God has to obey. And there's this kind of if you look at, for instance, Hilbert's list of problems, number 6 is the mathematical treatment of the axioms of physics. So there's a long tradition in mathematics that is just finding another set of axioms, as we have the axioms of number theory or set theory, and then we can create the physical sciences. But of course, there's an opposite point of view, that mathematics is not only a Platonic science, it's also an environmental science. The concepts of mathematics often developed in close, I would say, collaboration with the other sciences. There are many, many examples. Astronomy and the development of geometry, they went hand in hand. Mechanics, of course, and calculus. We definitely mentioned that being in Cambridge. You can think about symmetry and modern algebra, the birth of Galois theory and all of that. And I would say that the modern point of view is that the language of modern physics, quantum theory, quantum field theory, string theory, which we think is the ultimate description of nature. Nature is truly quantum mechanical, should in some sense inspire mathematics. It's the classical geometry and symmetry that have been so productive and mechanics, we all know, are in some sense illusions of our mind, because reality truly is very different at the deepest level. So I think the question, and I think this is something that Michael Atiyah saw earlier than many others, and encourages us all to think about, what can we learn from this kind of deeper form of reality? Now, that means a different kind of approach. So Nigel already mentioned the article of Jeffy and Quinn and the responses to this. And one very eloquent one was again by Michael Atiyah, where he's criticized this sanitized view of mathematics, arguing that if mathematics is to rejuvenate itself and break exciting new grounds, it will have to follow for the exploration of new ideas and techniques, which in their creative phase, and that's a very gentle description, are likely to be as dubious as some of the great eras of the past. Perhaps we have to now have high standards of proof to aim at, but in the early stage of new developments, which we prepare to act in a more buccaneering style. And this is, of course, from the buccaneer in charge of mathematics for a long time. I also liked Bill Thurston's response to that, his wonderful paper on proof and progress in mathematics. And of course, also we mourn the absence of Thurston, and he gives an example. And his example is, what is the right definition of a mathematical object? And he starts with something we all agree upon is very important, the derivative. And then he says, well, there are many ways to look at the derivative. We could do the formal definition. Actually, there is a mistake in the printed version of that epsilon delta definition, which is quite striking. But then we can think of it as a rate. And you think everybody has a concept of velocity. Immediately tells you can take the derivative of a vector valued function. You can think of it as a slope, as a tangent. Immediately suggests a function of more than one variable. There's the infinitesimal approach. There's the discrete approach. There is the symbolic one. You can take derivatives of much more complicated algebraic objects. It's the linear approximation. It's the microscopic view. And then he goes on, and at some point he says there's definition 37 that he really needed in a particular context. And I think there's this wonderful generalization of derivatives all around mathematics. Like, for instance, there is the concept of a derivative of a knot invariance by going from an overcrossing and an undercrossing and seeing the chains of it. So Thurston's point of view was that all these different facets illuminate the concept of a derivative and only makes it more stronger than perhaps the original formal definition. I also want to say a few words about truth and beauty, not only because it's the motto of the Institute, the seal of the Institute represents these two figures, but also since Michael has been writing and lecturing about it so much. In fact, even with his collaborators, particularly Sir Michael Atiyah, working actually on the neurological basis of mathematical beauty. Beauty for him was an important concept, and he often quoted Hermann Weyl, who we just missed. That Hermann Weyl said, you know, I always try to unite the true with the beautiful, but I have to choose one or the other. I usually chose the beautiful. Echoing the famous words of Paul Dirac, that it's more important for equations to be beautiful than to fit experiment. Now, we could debate for a long time what Dirac meant for this. But I want to actually also show the other side of that argument, which a very deep quote I appreciate a lot by John Wheeler, the Princeton physicist, who said that every law of physics pushed to the extreme will be found to be approximate and not mathematically perfect and precise. And his point of view that mathematical beauty should always have this opportunity to be enlarged and be improved. And we shouldn't kind of aim for kind of ultimate aesthetical senses. Of course, there's also Francis Crick famous saying that a theory that accounts for all the facts is wrong because some of the facts are always wrong. But beauty in mathematics, I would say, also comes in two different flavors. Now, there's the more universal beauty, the power of, say, abstract vector spaces or linear algebra, category theory. And then there's the more exceptional beauty, the objects that are unique, like the planktonic solids or the monster group or octonions. And I think each of us, you know, can identify with some aspects of these two kinds of aesthetics. Now, there is something that we could easily make a kind of a mathematical wunderkammer, you know, a cabinet, a wonder cabinet with these kind of exotica. And you know, there are many lessons in the history of mathematics that, you know, it's dangerous to be attracted to that kind of wonder. There's the famous, which I like to joke, Plato's standard model, his description of the 5 Platonic solids as, you know, being the 4 elements together with the 5th one, the quintessence. And of course, you know, often Johannes Kepler, famous planetary model based on the Platonic solids, is being wheeled in as exhibit A of this kind of wrong attitude of applying mathematics to physics. But it's very interesting that this Kepler model was destroyed by Kepler himself, by careful observation, by observing that the orbits of the planets were not circles, but ovals. And he was intensely criticized at this time for introducing this kind of ugly object. And he writes in a letter to an assistant to Tycho Brahe that he's been criticized. He said, well, it's although I've sinned with the oval I've left. It's like being punished for leaving behind one barrow full of shit, although I've cleaned the rest of the Augean stables. And of course, now we know there's a much more deep and beautiful way to see all of those as conic sections. And you know, we know that there's a beautiful, even SO4 symmetry residing in Newton's laws. And so this cleaning of Augean stables is a little bit of a theme. So in physics, I would say there are 2 ways in which we see beauty. One is to look at the very small. So obviously, there's a tremendous progress made in physics in reducing physical reality to elementary building blocks, like the standard model of elementary particle physics. And reduction is a great, powerful way to find beauty at the smaller scales. Another actually opposite trend is to look at large collections of objects, like the statistical mechanics of water molecules. Clearly, that description is incredibly complex, but there are beautiful mathematical laws of hydrodynamics or thermodynamics that emerge in the statistical limits. So these both limits, I would say, you know, are necessary. And if you look at physics, you can see that there is some sense the language, the modern language of physics, use these 2 concepts at the same time. Where we have the description of gravity in terms of the curvature of space and time at the very large. And we have the language of quantum theory, probabilities and superpositions and entanglement on the very small. And you could argue it's the geometric half of our brain, the visual right brain way of thinking, that we use to describe the very large structures. And it's the algebraic or algorithmic side of our brain, the left brain, that we use to study the very small. And that's a serious conflict of, I would say, two branches of mathematics. Now, I'm very inspired by this talk that Michael Atiyah, I think, is quite unique in that he felt at ease in both of these realms and actually was terrific in connecting both algebra and geometry in very deep ways. And so the two ways in which modern physics sheds a light on this is that there are essentially functors going from geometry to algebra, which is quantization, the association of quantum mechanical objects to quantum mechanical variables or amplitudes associated with geometric objects. We see a few examples. And there's an opposite trend where actually out of algebra, out of these large random or quantum systems, geometry can appear, which is, a very nice symmetric point of view, where basically I will be arguing that neither algebra as geometry can be seen as any way more fundamental, and that modern physics somehow want to bring a synthesis between these two approaches, the left and the right-hand side of a mathematician's brain. Now, of course, most of the really exciting work of Michael Atiyah was in the 1960s. And of course, from the point of view of the interaction between physics and mathematics, this was really kind of a bad time. It was a time where both fields were very much directed to the interior. In mathematics, we had the Bourbaki style of building the foundations. It was a very necessary phase with higher levels of rigor and abstraction. While in physics, we saw a barrage of elementary particle physics, and many people claim the end of reductionism. This is the famous S-matrix theory, where physics was seen as a black box that could not be opened. And Geoffrey Chew, who would lead this development, actually it was in Berkeley in the 1960s, was actually saying that the aristocratic structure of atomic physics should be replaced by a revolutionary democracy where every particle receives equal treatment under the law. So essentially, we're claiming there is no reductionism. So this is the famous quote by Freeman Dyson, who all sadly passed away last year, that in 1972, declaring the end of the divorce or the end of the fruitful marriage of mathematics and physics. And I would say these are famous last words, because right around that time, I would say this wonderful relationship started to blossom again. In terms of a caricature, the black box could be opened, and inside was the elementary particle standard models as we know right now. And the most amazing thing that this, Lagrangian describing these interactions in a very symbolic fashion written down here is entirely written in the natural language of differential geometry and topology. It's about non-abelian connections, about curvatures, about spinors of covariant derivatives. It's a language that any differential geometry would understand from the start. And so then in the 1970s, we saw this blossoming of particle physics and mathematics. And there's the wonderful dictionary that came out of a seminar in the early 70s at Stony Brook, run by Cian Yang and Jim Simons, that literally tried to build a dictionary between the gauge field terminology on the one hand side and or the physics here on the left hand side and the mathematics on the right hand side. And it's wonderful to see that this dictionary had some empty spots on the left and the right. And that, of course, was incredibly fruitful. And Michael Atiyah was like totally instrumental in convincing the mathematical community and the physical community that this is a fruitful direction. So for the purpose of my talk, I want to distinguish different kind of levels of understanding this physics-geometry connection. So I would say we start in classical mechanics, which in a caricature way is about describing how a particle moves from A to B, and it does so through a straight line or a geodesic. It's the language of calculus and geometry, of dynamical systems, development of chaos, or the very rich field of dynamical systems, broadly construed. If we move to quantum mechanics, of course, we have the famous sum over histories. In quantum mechanics, we have not a single path, we have an ensemble of paths. In quantum mechanics, one considers this ensemble, which is an incredibly modern mathematical way, not looking at the specific object, but I would say the whole category of objects. And we can see, brought, of course, the language of functional analysis, operator algebra, differential topology into mathematics. if we move to quantum field theory, at least perturbative quantum field theory, it's not about going from A to B, but you could start in A and end in B and C. Particles can split, they can be emitted and absorbed. And the creation and annihilation of particles gave a rich new structure in mathematics, fields that are typically called quantum topology, so the study of knots and 3 and 4 manifold invariants, Grassmannians, and what's now called amplitudology. I will come to that in a moment. And then there's a next level, which is perturbative string theory, essentially replacing particles by loops. It's going to the loop space of the manifold, broad conformal field theory, infinite Lie algebras, moduli spaces, mirror symmetry. And then I would say there is like a fifth level, which would be truly quantum gravity, where in some sense space-time itself becomes a quantum mechanical object. And it's not clear what kind of mathematical fields are involved in it, but we've seen in the last decades that areas like non-commutative geometry, sheaves, derived categories, the Langlands program all can find a place in this much larger program. Now, truly essential to this is this question: what is a quantum field theory? And I would say it's a unique local quantum system. It's a merger of algebra, that mean local variables, a gauge group in that representation, combined with the space-time geometry. And often I think of it as a bucket of paint that you can kind of you can paint a manifold by adding these local quantum variables to each point on the space-time manifold, getting the thing what's often called a partition function. Now, a classical field theory would typically be defined as a set of fields, which are maps of a manifold into some abstract field space. We have an action whose critical points describe the classical solutions, certain typical second-order differential equations. And then there is a moduli space of the classical solutions. Well, quantum fields would then be typically described by a Euclidean, for instance, path integral, where in some sense there's a localization or a semi-classical localization around the fixed points in that path integral, which are the modular spaces sitting inside this much bigger infinite dimensional space. And there is some like typical semi-classical approximation where h bar is typical Planck's constant. So this is what we see the traditional way to look at quantum field theories. And there's a classical limit where these saddle points dominate and the classical solutions are being recovered. Now, there are many, many reasons why this approach is insufficient and perhaps naive. Most important one is the concept of dualities. So there are ways in certain settings to study the moduli space, the space, the landscape of all quantum field theories. And then there's the phenomena that is a one field theory, F, can be related to a dual theory, F star, by picking a path inside the space of quantum field theory. So you can have a classical limit on one end being related to a dual classical limit on the other. This immediately creates a great ambiguity, because what is the fundamental field? Is it F of F star? Furthermore, there might be special points inside the moduli space which have exceptional symmetries, quantum automorphisms, and there might be even quantum field theory that do not allow for any classical limit. So they exist as quantum objects in their own right. So this means that we have to look at quantum field theory in not using, I would say, our classical intuition. Now, in classical mechanics, of course, we have a phase space, and we know in quantum mechanics the phase space is replaced by something else because the variables Q and P do not commute. I personally love the saying by Wolfgang Pauli. He wrote to Werner Heisenberg just 2 weeks after Heisenberg discovered his uncertainty relationship, and Wolfgang Pauli said, well, I understand what's going on. I can see the world with the pi, so the momentum I, and one can see it with the qi, that is the particle I. But if one opens both eyes, one becomes crazy. And I think this concept actually is still, is true in a much more, abstract level in our study of quantum field theories, because there are dual ways to look at quantum field theories, where we have the field theoretical version of a Fourier transform. A famous example is, of course, four-dimensional gate theories, where the classical solutions are instanton self-dual connections, and we have the famous moduli space of instantons, and we have an action and a gauge coupling. But we know there is a dual description by the electric-magnetic duality, where the gauge group G is replaced by the Langlands dual gauge group G dual, and at the same time changing the coupling constant tau, which essentially is Planck's constant generalized to a complex variable. These theories have a very rich duality structure, not only the large, small Planck constant limit, but even a full SL2Z. In fact, if you go famously to the so-called Waffa-Witten theories, the supersymmetric versions of gauge theory, the partition function turns out to be a modular form. So it has a very rich structure, and there is an SL2Z acting on the space of gauge theories that's totally absent from any classical or semi-classical description. And in fact, it turns out that these partition functions are intimately related to the characters of a two-dimensional conformal field theory. So somehow there's an elliptic curve hiding in this problem. In fact, that points out to another mystery, that these coefficients that describe the semi-classical contributions often turn out to be integers. In fact, they are dimensions of vector spaces. And that's also something that's totally absent from any, I would say, naive intuition about what a quantum field theory is. So this so-called categorification, an integer structure in the semi-classical expression is also another miraculous fact. In fact, you could argue that gauge theories are the first example where we see, in some sense, an emergent geometry. Studying the instanton connections on a 4 manifold, out of the study of that, we actually find the ingredients of a two-dimensional conformal field theory on an elliptic curve in the case of n=4 theories, but actually it can be generalized to arbitrary algebraic curves and the study of representations of infinite dimensional symmetry algebras. So I would say there are many ways to kind of problematize the mathematical structures of quantum field theory. It has turned out to be very difficult to make a constructive algebraic proof of a quantum field theory. It's the famous Clay prize. Even in the case of so-called asymptotically free theories, which are in best shape, there's a surprisingly rich structure in Feynman diagrams that goes far beyond what the physics suggests. There are Hopf algebras that seem to be relations with zeta functions and deep connections to number theory. There are the so-called twistor reformulations of certain quantum field theories, where the sum over Feynman diagrams is in fact much simpler than the individual diagrams themselves. The so-called amplituhedron appears there. So there is a magic in these perturbative expansions. As I said, there are these surprising integral structures, and it's intimately connected to the theory of exact quantization. There are the dualities, which are really baffling from a semi-classical point of view. And you could even ask whether the whole path integral and the concept of quantization itself make even sense. Perhaps quantum field theories themselves can be emergent objects. Now, there are various ways to more abstract mathematical ways to approach what quantum field theory is. We can start from an algebraic point of view in terms of the operator algebra of local operators, or the study of the scattering amplitudes. There's a more geometrical way by cutting and pasting manifolds, cutting most spacetime manifolds and gluing them together, considering the quantum field theory on various kinds of different topologies and calculate their indices, or introduce so-called defects like knots in 3 manifolds to study quantum field theory. And all of these methods are being actively pursued. Particularly in two-dimensional conformal field theory, of course, we know that the operator product expansion is a very powerful way to connect to infinite dimensional Lie algebras. And the cutting and pasting, as we just heard also by the talk by, beautiful talk by Nina, gives rise to the structure of so-called vertex algebras, the associative algebras underlying two-dimensional conformal field theories. It's the famous string product, the fact that two-dimensional algebras, two-dimensional field theories generalize what essentially is the intersection product in many cases of cohomology. So for instance, in topological string theory, where we study the space of holomorphic maps into a target space using Gromov-Witten invariance, we can build this kind of generalization of the classical intersection product. The classical intersection product, of course, in a 3 manifold is the intersection of two-dimensional spaces in a point. And the quantum version of that, the quantum cohomology, actually looks at rational rational curves inside the space X that intersect with three of these kind of forms. And that's the famous quantum cohomology or quantum intersection product that appears. So there's a rich story there. But I want to say something that, there's essentially another way to look at these kind of ways in which quantum theory has impacted the study of geometry. Now, what I was just describing, this study of loop spaces and mirror symmetry, you can think of some kind of stringy form of geometry, where many of these symmetries, dualities like mirror symmetry take place. But as I said in the beginning, there's a deeper level of truly quantum geometry, where geometry itself should be an emergent quantity, which is much more based on non-commutative quantities, where physicists would draw these kind of bizarre diagrams of space-time foam, where space itself becomes a quantum mechanical object. And I think that actually is perhaps at this point the most exciting way in which geometry and algebra are intersecting. So in physics, this all came through the study of so-called open strings. So open strings are maps of intervals into a certain space-time manifold that could end on a so-called brane, or mathematically often a sheaf. And these branes can come with a certain multiplicity. And by studying multiple branes, you can have essentially open strings that are beginning and ending on different copies of that particular object. And so you, in a very natural way, are led to consider a matrix, so a non-abelian structure, a non-abelian gauge field. So within string theory, there's this opportunity to study non-commutative objects in a very direct way. And there's kind of an intuition that says that studying these non-commutative objects in the limit, when the number of these objects is very large, so when n, the number of branes, goes to infinity, that should be equivalent to essentially studying a curved space-time with some kind of emergent gravity. So the intuition here is that, if you study these kind of open string or gauge fields, you can use this kind of ribbon graph diagram, where essentially, the vertex that describes the interaction of two of these open strings is just matrix multiplication. And then if you study many of these open string diagrams, effectively, my animation is not running, then actually you would effectively see a closed string. So essentially an open string diagram with many, many different holes should be equivalent to a closed string world sheet. Now, this actually has a beautiful role in, I would say, the Atiyah-Siegel axioms of, or originally conformal field theory and then topological field theory, but I would say now much more general approach to quantum field theory using the language of category theory. So from that point of view, we're like in codimension 0, a quantum field theory will associate essentially a complex number, a partition function, to a space-time manifold. If in codimension 1, we have manifolds with boundaries, and the language of category would associate a vector space, a Hilbert space of states, to the codimension 1 boundary here. And of course, then the famous gluing laws that describes the composition of these morphisms. Going down to another codimension 2, you will have a category of boundary conditions. So that's why a very rich mathematical language gets introduced by considering these open strings, where essentially the composition law of morphisms in the category is now the non-abelian structure that's there in the composition laws of these, in the gluing laws of these open manifolds with boundaries. So I've depicted here in 2 dimensions, but you could do that in arbitrary dimension. Now the gauge gravity duality is incredibly rich because it again, it connects on the one hand algebraic objects like derived categories, non-commutative spaces, vector bundles, K-theory, to geometrical objects, metrics and curvatures, the infinite dimensional Lie algebras we saw before, like the Virasoro algebra, loop spaces, and the genius expansion that comes, it's part of closed string theory. So in many ways, you can think of the Atiyah-Singer index theorem as perhaps the first instance of this duality. It's the index theorem you can see as connecting algebra or analysis on the one hand side, on the left hand side here, the index of the Dirac operator, to the geometry and topology on the right hand side. And so a physics proof of this index theorem would go by considering this particular string diagram, a cylinder that begins and ends on a D-brane. A D-brane describes here the particular vector bundle. So we have vector bundles E1 and E2. By kind of looking at this diagram, in one direction, you can think of it as a thin strip going around a circle. The Hilbert space associated to the strip would be essentially the Hilbert space from which the Dirac operator acts, and taking the trace essentially computes the index of the Dirac operator. Now, changing this, actually, we could look at the diagram from another perspective, with time not going vertically but horizontally. And then you can see this as a map which takes an initial state, represented by the vector bundle E1, that travels and then ends in a final state, represented by the vector bundle E2. And the equivalence of these two diagrams is then a cartoon version proof of the index theorem. Well, this goes much, much deeper, and I would say perhaps the most familiar, or perhaps the first instance of this phenomena actually appeared already in the 1940s when Eugene Wigner studied random matrix models. Wigner, of course, famously studied the Hamiltonians of very complex systems, atomic nuclei, which are incredibly difficult to study. And he was wondering what the spectrum of such a big Hamiltonian, such a big matrix is. And he had the brilliant idea to instead study an ensemble, a Gaussian ensemble in his case, of such objects, and took looked at the distribution of the eigenvalues, what we now call in physics at least the 't Hooft limit, which means at the same time as you take the rank of the matrix to infinity, you take what in string theory would be the string coupling constant, or you could also call it like h bar, G string, or h bar, the width of the distribution to 0, keeping the combination of the two fixed. And Wigner, of course, famously found that the distribution of eigenvalues became a smooth distribution and had this kind of very sharp cutoff at the edge. So he discovered a shape, a geometric shape, his famous semicircle, in this particular limit of the statistical limit of this large n limit. And in fact, you can actually study this model not taking n to infinity, but keeping n finite and doing the so-called 1/n expansion. And modern language of string theory tells you that all the coefficients in that expansion actually make sense. You get a geometrical expansion. The leading term is Wigner's semicircle, but there are subsequent terms, perturbative terms, that also can be described in terms of the geometry, the emergent geometry that he found. Well, I won't go into the details, but if you, for instance, study general matrix models with the general potential, you have an eigenvalues that are condensing or sitting in multiple vacua, and you get a more complicated curve. In fact, you get a so-called spectral curve that's not a circle, but once complexified, is a hyperelliptic curve. So instead of a rational curve, we get arbitrary hyperelliptic curves. And it's the geometry of the hyperelliptic curve that actually encodes the 1/n expansion of the matrix model. And you can think of Wigner's circle as being essentially this cut, this real cut of a complex curve, a complex spectral curve that actually is describing the simple Gaussian model. So in the study of these Wigner models, you'll find an emergent spectral curve that appears at large n, but at finite 1/n expansion, you can describe in terms of the geometry of that space. But of course, you can also study these matrix models by taking n finite, and in some sense, there's no geometry at all. It's an entirely algebraic object. So I want to end by not any firm conclusion, but making some general remarks. So I think Michael Atiyah showed already in the 1970s that it's tremendously productive to restart this conversation between mathematics and physics. And it has been tremendous success. I think it's hard to think of any area, both in math and physics, that has such a constant rate of return in terms of the initial investment. So it has reproduced many, many wonderful results and really path-breaking proofs of theorems. But in some sense, I think that it also showed that mathematics and physics do not commute, in the sense that originally, I think many of the physicists thought that mathematicians can clean their Augean stables and make mathematically rigor the fuzzy logic of their physical intuition. I think this has hardly happened. What we have seen is that mathematics has picked other ways to prove some of these conjectures that came out of the physics literature, and have a very different language to prove. So the physical intuition which is perhaps more like mathematics by night, is not the same thing as the mathematical rigorous proofs, which much more the mathematics by day. But of course, there's a long tradition. Here's another colleague of Sir Michael at IIS, André Wij, talking about the importance of metaphors and the kind of fuzzy nature that these blurred reflections that help you go forward. And so I think this idea that he wrote quite briefly here, that the twin theories reveal their common source before disappearing, is in some sense also very much true about this chapter in the study of geometry and physics. So I think in some sense this field is very much like a mathematical program, as we have in arithmetic geometry, or the Langlands program connecting the study of automorphic forms, a number theory on the one hand, and the study of geometry in the other. André Wij famously used the metaphor of a mathematical Rosetta Stone, and I think now quantum physics is in very much of a similar nature, of describing these kind of various phenomena in different texts, with perhaps a large part, particularly of the mathematical text, still missing, and I would say also the foundations of the physical text missing. But one of the most baffling, I think, developments of this whole field is that there is this wide variety of subjects and mathematical languages that play a role in studying modern quantum physics. I'm just producing some of them here, but clearly it looks like that physics is as they say in American English, throwing everything at it except the kitchen sink. That there's hardly any mathematical tool that is not being employed and used in the study of quantum theory without any of them being predominant. So it's a little bit like the definition of a derivative that Bill Thurston used to explicate the nature of mathematical objects. So I think there's a very deep question whether there is something unified there. Is there something like quantum mathematics? As I said, 100% of reality is based on quantum theory. Could something similar true for a large tract of mathematics? In fact, it's almost an epistemological question. Do we understand nature, reality, in terms of essentially a set of coordinate patches and transition functions, these kind of theories and their dualities, the various algebraic and geometry ideas? Or is there something like a global manifold? Is there a global definition of what it is, an axiomatic definition? And I think the jury is still out. So I would say, the situation right now is that, we have this classical image, really classical, coming from Plato, of us just seeing the physical shadows of mathematical real objects that are in a dream world and cast their shadows, and we only are able to see the shadows of these perfect objects. So I would say that Atiyah's dream is almost like the opposite. He's taking these very fuzzy physical realities and saw very early that they cast these very precise mathematical shadows in terms of very strict and crisp conjectures, hints of deeper mathematical truth that can actually move away from this physical reality and go in very different directions, higher dimensional spaces, perhaps number theory, different fields, etc. which has been incredibly enriching. So let me just end by saying one other word of Michael Atiyah, which has been for me personally such a great friend and mentor. One of the sayings that I think is always misattributed to Winston Churchill, that if a person isn't a revolutionary in his young days, doesn't have a heart, and if he's not a conservative in his later days, he doesn't have a head. So I would say in general, our personal lives are often described by, I would say, a decreasing exponential function. So there's a negative exponent in many ways. I think Michael Atiyah is the happy exception to that law of nature. No, he was actually even more revolutionary in his later days, and it was clearly his life had a positive exponent. I think that's is a wonderful example. It again showed that he was in many ways super generous, and it's wonderful to have to learn to know him as such a close friend, and thank you so much for inviting me to speak at this wonderful occasion. So thank you very much.
Ooh, questions. So thank you from Tony Gardner. I had a question over here in the hall.
I was curious about your picture of the local geometry versus the global picture, that map you had.
Mm-hmm.
What does that have to do with quantum mathematics?
So I would say that in many the way we describe, for instance, certain objects in say quantum field theories is very much like we have these two, for instance, as I gave an example in gauge theories, there are two equivalent descriptions, like an electric description and a magnetic description. Both have very well-defined variables. There's a choice of gauge group. There could be even a choice of a representation. So, and there's a semi-classical perturbative expansion. And that would be one map in the atlas. And then there's a dual description using the dual gauge group. But you wonder, of course, for instance, if you would have a constructive proof of such a gauge theory, can you define it in a way that is where both the electric and the magnetic variables are visible? So we know, for instance, in quantum mechanics that we have an abstract formulation in terms of a Hamiltonian acting on a Hilbert space, and then there are two bases of the Hilbert space. There's the position and momentum representation, and we know there are dualities, Fourier transform to go one to another, but there's an infinite set of other bases, and there's in some sense a coordinate invariant description of quantum mechanics. I think we lack, for instance, in the case of quantum gate theories, we lack such a coordinate invariant description. And honestly, I don't know what the final answer will be, but anybody who will claim that one specific, say the electric description of a gate theory is the right one, should be wrong, because you can easily describe exactly the same kind of mathematical structure from a dual perspective. And so I think we are really struggling. One way to say to rephrase this again is that in a global definition, one aim could be that the quantum dualities are completely explicit and aren't kind of a surprise. Or for instance, these integral structures that sometimes emerge are completely explicit. So often I think we can show by calculation that our objects satisfy certain symmetry properties or integrality properties, but there isn't a truly fundamental way of understanding why they have these properties.
But sorry, just to press a little bit more, could you say in a sentence what that has to do with a notion of quantum mathematics? That's what I'm trying to.
Yeah, so I would say that the language that we would need to study a quantum field theory that actually makes these symmetries completely explicit. So my own guess, but again, is that we are just lacking the mathematical concept to make such an definition, I would say axiomatic definition, that truly makes sense. So I think the way we're thinking right now about many of these quantum objects is through a semi-classical point of view. So our manifold is a classical manifold, our fields are connections with curvatures and vector bundles. But that's all kind of a that's good, that all works, I would say, in one of these coordinate patches. So we have to make it more explicit. And I think, you know, in that sense, the Langlands program is a fascinating guide, because in the Langlands program too, I mean, it's very difficult to see the dualities on a very in an explicit way. And also, I think there we are still kind of searching for the right mathematical concepts. And so a miniature version of this question is, you know, try to define in an axiomatic way some of these structures so that the symmetry properties of the object are explicit. I mean, that's something that, you know, the globe that's rotating here on the right-hand side has. So it clearly suggests an SO3 symmetry. So the question is there a definition that would be a small version of that question. Is there a definition of these quantum objects that at least make their symmetry properties completely explicit?
Good. Okay, thanks. Any more questions? Nick?
I mean, as you alluded to, and you well know, the standard model of particle physics described by the quantum field theory is a very rigid, exceptional object, at least as we understand it today, you know, with the SU3 and the SU2 and the U1. It's a bit like Kepler's picture with very specific numbers. And then when you have introduced the quarks, there are precisely 6 of them and so on. That sounds a bit like Kepler's picture. And yet so much of your talk alluded to the idea that, you know, geometry is random, that, and as you know, what you mentioned, that the brane picture for SU3 requires 3 parallel branes rigidly glued together. That seems, from your sort of more random perspective of random geometry, extremely unnatural. I wonder whether you have sort of comments on that.
Well, thank you, Nick. That's of course a question that really, you know, goes to the heart of all the debates that are currently within physics. So on the one hand, indeed, the standard model is rather beautiful, and as you know, it easily fits into a larger gauge group like SO10 with a single spinor representation, and SO10 can be in many ways seen as E5, so it fits even in the icosahedron, you know. So in some sense, it's a very exceptional structure. On the other hand, many of the parameters of the standard model, particularly, you know, the masses and gauge couplings, seem to be as random as they could be. And so I would say that, you know, the physics community is divided between these 2 points of view. And certainly, I think string theory in the 1980s and 90s was very much on the Keplerian point of view. And, you know, I remember well at the very early days, actually, I was still a beginning graduate student, that our professor said, well, within a week, we will calculate the mass of the electron. And I felt, well, that's interesting. Physics is done just at the moment when I start. And that was the time when we thought there might be 2 Calabi-Yau manifolds. And now we know there is, to all practical purposes, an infinite set. So I would say, no, there is a countercurrent in string theory that says that, you know, no one should actually study the so-called landscape, the space of all quantum field theories, and see whether there are any kind of patterns there, whether it's not clear how that landscape looks, how many of these, let's say, effective quantum field theories also exist as theories that truly have a rigid mathematical definition. But now, if I would say, you know, in history, often I think the line of arguments is that one often starts thinking like Kepler in his early years, and then one finds the equivalent of the oval, and you know, destroys that sense of beauty, and, you know, gets a very different kind of abstract level of beauty. So if you can criticize fundamental physics, it's that it hasn't really made up its mind which kind of the 2 approaches is the most fruitful. And I must say the standard model is very conflicting because it gives these dual messages. On the one hand, it seemed to be a rather generic quantum field theory. On the other hand, it almost begs to be a part of these exceptional Lie groups. And so anybody who loves the octonians usually also sees a way to connect it to the standard model. So I would say we are in a mixed state.
We have a question from Roger Pickin. He asks what you would consider Atiyah's most visionary contribution after K-theory, and whether that might be the axiomatization of topological QFT.
Well, I think that's a very good point. I think that was really extremely helpful and beautiful. And I must say, it's one of the things that has like vastly generalized. So one thing we have seen is that using the language of cobordism theory, which I noticed, I noticed, for instance, in my own work with Edward Witten on discrete gauge theories, we only felt comfortable mentioning the concept of cobordism theory in a footnote in our paper. And now actually really applied physics that's studying topological insulators are studying, really very rich equivariant cobordism groups, because actually this axiomatic point of view is, I would say, at this point, the most powerful way to have something close to this kind of global perspective on quantum systems. Of course, it only leads to real classifications in limited cases, but not only that has been very fruitful, it has also been used in very concrete application. And so I think Michael would have been very fun to see that this line of thinking is now being taken over by branches of physics that are very, very far removed from abstract mathematics and studying actually physical systems. And in fact, we see the power of category theory and classification, because if you know there's a list of possible quantum systems, then people will start going to the laboratories and trying to actually make these objects. Because there is a kind of a mathematical existence proof. So I would agree that it's one of many. I think the most important contribution from my point of view has been pointing to this kind of rich dialogue between physics and mathematics, and opening up the eyes of mathematicians to be tolerant of the fuzzy thinking of physicists, and similarly opening up the eyes of physicists to be tolerant to the rigorous thinking of mathematicians.
Okay, and on that note, I think we should thank Robbert again. Thank you very much.